what did we see? So now we tried to consider this picture from a more broad perspective, from the perspective of Bayesian estimation, where we really take the prior distribution of the parameter into account and want to say more than just the Cramer-Rao bound, right? And we've seen that there are still some, at least in some restricted cases, where we have projected measurements. We can get some general results. Nevertheless, this still doesn't tell us the answer, right? We would like to have some compact answer. You can say, okay, so what is the limits of this estimation, right? This is what we're going to try to say now. So in other words, okay, we have this formula now, which we have to compute, but in principle, we just have to compute it every time, and it's not clear how the size of the probe, for example, is related to the results we're going to get here. Just one thing you should remember is the Cramer-Rao bound is still remains true, right? This is kind of trying to go for a refinement of the Cramer-Rao bound. It's still true that the mean squared error estimator of the estimator of the field here, in the sense that the deviation of the estimator from the true value, right? This is still upper bounded by the Fish information of rho for at any value, at any point of this curve. So this is still true that the Fish information is an important figure of merit for estimation in the Bayesian scenario, because we cannot beat this bound, right, just by considering the prior. But this is what we're going to see now, is that there is more to it, right? This is not the only ingredient. This is kind of the local ingredient of how well I can resolve the neighboring values of the field. But there is another catch, and this is interesting, yeah. So let's do this now. And what is that? In other words, the question is, what is another ingredient which comes here and allows us to do a good Bayesian estimation, right? And for this we need a tool from last semester. Okay. So actually, what we're going to do now is we are going to use the Kolevo bound, which we've seen last semester, and we want to use it to we will interpret it in the context of estimation, right, of quantum estimation. So for those of you who were not here last semester in the lecture, right, I know there are several persons who are not here. I will recall the Kolevo bound quickly, but we don't have time, of course, to go again into information theory, interaction information theory, so entropy and so on, in the sense of information transmission through channels. So I'll just give you the result already in a quantum version. The only thing you need to understand is like kind of some notions of what an entropy is, right? I mean, I guess you know it already. Everybody knows what an entropy is, either from statistical physics or from information theory. Anyways, there will be like no question exam about the Kolevo bound, but on the implications, yes. So I will also send the note from last semester. So for those of you who want to read in details how to prove this bound or get a bit more knowledge about entropies, we can refer there. So the Kolevo bound, what it tells us, first it looks like it's a different context from what we're doing here, but then we'll see that it's actually related. So the Kolevo bound is a statement about the following scenario. Let's say we have Alice, right? So we have Alice here, and we have Bob. Okay, and Alice is it wants to send some message to Bob. Okay, so to do so, again, Alice prepares her random bit y. She has a random bit y, right? And she prepares it with a probability distribution p of y, right? So y can take values, let's say, I don't know, from some values. It doesn't matter. Y, let's put the values. Let's say y can take values from 1 to m, right? So y can take m different values, which are distributed accordingly to this distribution, py. Actually, we can put already p0 of y, and you probably can guess already why there is a 0 here. Now Alice, she wants to send this message to Bob, and to do so, she encodes the quantum state, rho y, right? So she takes this value y, right, from this alphabet with this distribution, and she encodes it in the quantum state. And then she transmits the quantum state to Bob, okay? Now Bob, what he does here, he receives a state, he receives some state. Of course, he doesn't know why. He wants precisely to read out y from the state he receives. So what he does a measurement. He does a PY measurement, some PY measurement, let's call it EX, right? So X are our PY measurements, and we'll call it, so let's say X runs from 1 to n, right? Potentially there is different n than n. What does he do? So then he gets the outcome X, right, as an outcomes label, and then of course the probe, so he gets this outcome X, and we'll call this now random variable big X. Right? So X, this is just a random variable which is the output Bob gets. Now the question we're interested about in this business is how much information can Alice transmit to Bob by doing this. Okay, now in this context where we're talking about channel capacity and information transmission, the important figure of merit are entropies. Okay, this comes all from the Shannon coding theory and so on. And the entropy, you know, I mean, so the entropy of a random variable, so we'll denote it H. So the entropy of a random variable X, Y here, right? This is just given by minus sum of the probability to get the outcome Y times the log. So I guess you all know it, right? Times the log of this probability. Yeah? This is the entropy for random variable. Why now for a quantum state? If you have like a quantum state, now we can also define an entropy. This is the Shannon entropy. Now for a quantum state, this will be a von Neumann entropy, right? Then this is minus trace of rho times log of rho. Okay. So in other words, of course, if you think of it of rho as being, if you diagonalize it, we go in a bit more diagonal, then rho just has a probability as elements of the diagonal. Then the Shannon entropy of a density matrix, sorry, the von Neumann entropy of the density matrix is equal to the Shannon entropy of the probability distribution, which it has on the diagonal, right? Very simply. Yes, so entropies. I guess you know it. Those who were here last semester for sure know it. Don't have an excuse to not know it. Alright, so what does the Haleo bound tell us? Now we have this entropy and we have the thing. So the Haleo bound actually it tells us something about the mutual information. So here let's tell the Haleo bound. Haleo bound tells us mutual information about, so this is denoted I, or actually H, mutual information between X and Y. So this mutual information we can just write it down as H of X on Y. This is the entropy. This is the entropy of X. Yes, so of Y, sir, of Y. So the entropy of Y is basically how uncertain we are about the value of Y. Yes? So the entropy increases. So just to recall you, so if Y would always take one value, right? Deterministic value, for example, Y is always equal to the first value 1, then the entropy will be 0, right? There is no ignorance we have about this one. But if it's the maximal entropy a random variable can have, then it's completely uncertain. So when all the values from 1 to n are equally probable and given by probability of their occurrence is given by 1 or n. So a flat distribution is the one which has the least error. Right? So mutual information is the entropy of Y minus the conditional entropy of Y on the value of X. Okay? Let me just first write what it is. So the conditional entropy of Y on X, this is given by the following thing. It's sum over all possible, it's sum on the probability of X. So again, as you know, just last hour we had this probability of the outcome. So for each outcome, now Bob has some knowledge, right? Times the entropy of the conditional distribution of Y on X. So it's very, you see like kind of similar things appearing that we just had previous hour. So what is this here? Now, for Bob, you see, a priori he knows what is this distribution P0 of Y. Yeah? And this distribution is characterized by this entropy. Right? So this entropy is like how uncertain everybody who knows the preparation is about the value of Y. And now this thing here, this is a conditional entropy. So this is actually how much Bob ignores the value of Y after he measures X. Okay. So for example, if Bob measures x, and from his measurement he knows that actually this x can correspond to only one possible value of y, well, then this will be like just a Kronecker delta distribution here, so the entropy will be 0, and then we subtract nothing. So in this case, actually, originally Bob ignored that much of Alice's value, but afterwards he knows it perfectly, so the entropy is 0, so he learned this amount of information, right? That's why this is called mutual information, so, right? So it measures how much ignorance of Bob about the value of y dropped after his measurement, right? So it's really the entropy after the measurement, the average entropy after the measurement, here is subtracted from the original entropy. Right? So it's really how the entropy drops through this information transmission protocol, yeah? Yes, so that's what on the left-hand side of the Kleber bound, this is this mutual information, and on the right-hand side of the Kleber bound is something now which is quantum. This is what the Kleber bound tells us. So, the uncertainty, so the mutual information of y, this cannot, so this information cannot exceed the Shannon entropy of, you see now, sum of P0 of y rho y. So this is the entropy of the average set, so to say. So we just take these possible quantum states which Alice sends to Bob, and sum is the probability distribution. Minus, we have to subtract now, actually kind of the conditional, no, it's not a conditional, sorry, it's different, because this is not conditional, but it's conditional. So minus the average entropy of the sent state. Yeah? Now we'll consider a bit a restricted version. We will just say that Alice always sends pure states. Because entropy, right, and entropy here, it's always positive. So of course this thing is smaller or equal than just S, the first term, right, because we subtract something positive. So this term is equal to P0 y times rho y, the entropy of this guy here. And in fact, this thing is 0. If Alice always sends pure state, then this phenomenon entropy here, right, is this phenomenon entropy is 0. So in the case where we have a scenario where Alice only sends pure state to Bob, this bound is also tight. So that there is a scenario which achieves it. Okay. In summary, this is really what we care about now. Right? This is a Kleber bound for us. So now again, as I told you, because we didn't see the derivation of it, and I guess maybe you're not some of you are not very familiar with this entropy, we just take it for granted, and we'll see how we interpret it. Okay? We see how we can interpret it for our task now, for our Bayesian estimation task. Good. So Kleber bound tells us about the entropy of this object here. Tells us something about how much Bob can learn about Alice's value. Okay, so let's write it down here, because we're probably going to use it a bit in a moment. Entropy of sum of y, py times, well, let's write p0 of y times density matrix Alex sends for y. This is a Kleber bound. Good. Yeah. Yeah. Question now. Why can we relate it to what we are doing here, right? Because a priori this is something different. You might say, you know, there is like somebody sending information to someone else. Well, in fact, it's not so different, because at the end, the only thing which matters here is that Bob receives a state, a quantum state, that depends on y. Yes. So in particular, now, if instead of, so this thing we can also kind of lift it to continuous distributions, not just discrete possibilities. We'll say more on this a bit later. Yeah, then just not say instead that really Alice has a prior distribution P of y, right? And she sends, so in other words, no, let's just do it differently. Let's just replace y by b. No, just say y is b. We just call it b. So now here we have kind of a prior distribution of b. So this is the probability distribution that b takes some value. This is like a prior distribution for Bob, because Bob knows how this probability distribution looks like. Yes, but and then Bob receives a state b, and what he wants is precisely to measure x and to observe an outcome. For measuring x, he wants to reduce his uncertainty about B. Right? So this mutual information here of X on B in this case, right? So I'll just change it here. B here, right? This will measure in terms of information, also in terms of entropy decrease, how much Bob, after his measurement, learned about the value of the field. Yeah? So it's actually the same scenario. Just instead of Alice here, we will replace it by the environment. Yeah? So Alice can, the role of Alice will be played by the environment. Yeah? So in other words, it's really kind of, we put our initial state receiver here, it interacts with the environment, and then the environment does this encoding, and then we measure out the value of the parameter. But this is one thing, but of course, we'll come back to this again. The other thing is that this Huleva bound is in terms of entropies, and we typically care more about the variance. And that's an interesting difference we will discuss shortly. Yeah, but now let's write this thing explicitly down. Yes, so what is entropies? We will discuss both sides of this inequality here. So first thing is mutual information. Mutual information. So what is the mutual information now of X on the field? As I said, this thing in the case of discrete values of B. So I'll start with this because it's more natural. Well, this is just given by the entropy of the B. So in other words, let's write now really B is a random variable, right? So it's the entropy of the prior distribution of B. It's the entropy of B, so it's given by this distribution, minus sum of P of X, right? Minus the conditional entropy, times the entropy of the distributions P of B conditional to X. Yeah? And here you see already we have precisely the thing that we were discussing, right? So we have our prior distribution here, we have our outcome probability, and we have the conditional distribution after we updated the thing, right? So this is really the distribution of B conditional on the observation of X. Yes, so let's, how to do it? Well, let's write it down, this is entropies down explicitly, yeah? So this entropies, I changed the color because I think blue is less visible than black. I'll close the window as well, this is some music. Yeah, so we'll just take the definition of this entropy and we get this entropy here is just sum of B, right? So now we'll start with discrete values of B, so we'll see discretized times P0 of B times log P0 of B. So let's just call this value Bi. Okay, so what did we do here is basically we take our range of B and we divide it, so we have some prior distribution here, we divide it in small intervals like this. Alright? And then the probability of B, so probability of Bi, this is equal to B at value I times dB. Right? So times how big the sink is. Okay? Minus we have sum of P of X, and then we have the same story here. This is over X, sum of B of I, or Pi, the values of, yes, P of Pi conditional of X times log of P of Px, Bi conditional of X. Now there is actually a catch because we want to go from discrete distributions, like we discretized here, to continuous distributions. So we want to replace it by an integral. So what is P, again, as we said here from the small thing, what is P0 of, so what is probability of Bi? Well, in a discrete sense, right, so this is just a discretized version. This is actually probability of B times dB, right, times times how much we discretize here, right? So we take our dB here. Yes, small interval. So the probability of the field to fall inside this interval here, this is given by the value of the function here, the probability times the width of the interval. Discretized version of this continuous story. right? So what we have here is, I'll just plug it in both of these guys here, and we get something sum of bi P0 of b times db, right? So this thing is here, times log of P0 of b times db. You see that kind of there's a small problem because we have something potentially small here. Yes, plus sum of x, p of x, sum of b, p of bi x now db, and same thing here, log of p of b x db, right? Now what we want to use, you see there is a problem here because here we have something super small, but instead we want to recover a continuous version of the entropy, so here we'll just write log of, so we'll just expand the logarithm. This is log of p of 0 of b, right, plus log of db. And log of db is something going to, because this guy goes to 0, so it's something going to minus infinity. But the nice thing is that we subtract the two infinities here. So for the conditional, for the mutual information, it doesn't matter, right? So let me just write it down here. If we do this trick, we will just end up with sum of b db times p0 of b log of p0 of b plus, and here again, minus sum of db p0 of b log of db, which is a problematic term. And here we get sum of b of x, sum of b, p of b, conditional on x, log of db here, log of p of b, conditional on x, plus sum of px, sum of b db, p of bx, log of db. Okay. Now, what happens here is that db is doing the size of the interval, right? So this sum of b, this gives 1. So you see basically that these two terms, they cancel each other. So now we can safely write our continuous version of the entropy, right? Because since we remove this stupid terms, we can take the limit here, db going to 0, and this sum simply becomes an integral. It becomes an integral, and we just have this story. So we can now write this mutual information in terms of what we care about. Alright? Yeah, not this one. This is somewhere x. This one becomes an integral. So what I just wanted to tell you is that this thing, this entropy difference here between the prior distribution of the parameter and the distribution of the parameter after observing the measurement result, right? This is really given by the intuitive formula integral of db p0 of b times log of p0 of b, yeah, the minus sign for the entropy, plus sum of x, p of x, the probability of the outcome, times the continuous version of the entropy for the conditional distribution. Log of p of b conditional x. Yes? Yeah, so anyway, this is what you expect when you see such an expression, right, for continuous distributions, I guess. So, yeah, that's very nice. So we see how to interpret this basically, right? So we had, in other words, what we had some again as before, we had some prior distribution, right? So prior distribution of the parameter b, it's like a potato like this, but it has some entropy, right? So some uncertainty associated to it. Then we measure it, right? And for the x we get something like this, right? So we get a narrower distribution, or at least a distribution which has a lower entropy, okay? So we see how to interpret this part now, right? With our continuous distribution. This is really just the difference of these two entropy. So one thing you should realize is that, of course, this is also a valid cost function, right? So the entropy of a distribution, it's also a valid cost function. We use the variance because we care more about the variance. There is a reason for this. Maybe we can discuss it later on, but okay, no, because for example, something which can, so the entropy is independent of the permutation of the outcomes, right? So in other words, if you have, you know, a distribution between, so this distribution, right, where we just have a value here or here, this distribution has exactly the same variance as having a distribution like this, right? So the value of the parameter is here or in the neighboring one. So for the variance they're very different because obviously this distribution has larger variance, but for the entropy they're the same. Right? So in other words, if you want to, if you want to encode this information, transmit it through internet, and you have such thing, this will take you exactly the same amount of data, and we'll transmit this one. Because we really don't care where they are here, as long as they're just two possible values, right? But for the variance, it's very different because for the variance, it's a physical quantity, whereas the scale of this B really plays a big role. So this is we'll come back to this just afterwards, and we'll do the exercises as well. But otherwise, it's also a valid cost function, right? All right. So yeah, that's for the left-hand side of the Holevo bound. Now, what about the right-hand side of the Holevo bound? Well, for the right-hand side of the Holevo bound, what we get is the entropy, right? You see, so how much information Bob learns by measuring by observing X is bounded by this thing, and this is sum of Py. Or no, in our case, so this will be the integral as well right now. This is just really the average state we get here, right? So it will be the same story. P0 of B. It's a density matrix here, right? That we get. So in our case, it will be this times rho of B, rho B. Yes, this is the entropy of the state. Yeah, which is, should remind you, this operator gamma we defined just the previous hour, right? This was precisely this operator, the average density matrix. So this is just right, and so that's an average state. So it's also a state. Gamma has all the properties of a state, right? So it's positive. Its trace is equal to 1. One thing we can ask. So let's say we have the probe, right? So first question is we have a probe on it. So the probe is a d-dimensional system, right? Is a d-dimensional system. Okay? So if the probe is a d-dimensional system, what is the maximal entropy we can get here? Yes? So what is maximal Q? So what is maximal S we can get? Yes? So in other words, it's simple because this object is just a state, so we have like now a density matrix gamma, which belongs to, which is kind of a bound operator on this Hilbert space of the dimensions. So what question is now, what is the maximal S gamma we can get? Yes? For all possible gammas. But to answer the question, right, if you know, so yeah, to answer the question, just we know the entropy of this thing, right? This is just equal to the maximal probability distribution on the diagonal of the entropy, now the Shannon entropy of this probability distribution. Yes, where by doing this we just take gamma. State gamma is P1 to PD. Right, this is a state like this. So we just this is the eigenvalue distribution of this state gamma. And yeah, well, we know actually what is the maximal entropy of a probability distribution with the outcomes. Well, this is just we just need to take the most uncertain distribution, right? The most uncertain distribution which is less predictable. And of course, this is just a flat distribution, right? So this, let's call this M. So this M, otherwise it's just given. So let's know this. The M is just the entropy of a distribution which is 1 over D, right? And D terms like this. 1 over D. Yes. So when we compute this entropy, it's simple. minus sum of I equal 1 to d of 1 over d log of 1 over d. Yeah. Which is d times this, so it's just minus log of 1 over d, or simply given by log of d. Okay. So that's already an important message, you see. What does it tell us? It tells us that this entropy cannot, it's really ultimately the information we can collect by a probe, we can encode on a probe, and the information we can learn about the parameter is ultimately bound by the dimension of the Hilbert space, yes? On which the probes are. Alright, so the next question is then, does entanglement help to boost this information, right? Does entanglement help to boost this information? And this is, but to answer this question, of course, we need an encoding now. We need to specify how these states depend on the parameter. So let's now do it by means of an example. We will again consider this Hamiltonian encoding. Yes? So at the time. So yeah, so we have 10 minutes, something like this. Yes, so we'll maybe first make the connection to the variance. Yes, so now we know more details about these things, right? So really we have the entropy of our prior distribution. This is the how we interpret the Haleva bound for our purpose is that the entropy of this prior distribution minus the average entropy after we do our measurement. So P of B conditional mix. This is bound by the entropy of our average. In fact, one thing which we care about is, so let's look at this object, right? So already we know something from this, but let's make a connection to the variance of this distribution. Yes. So well, this is a constant. Yeah. So the entropy of a prior is just a constant. We know it, and this is, let's call it H0. We'll call it H0. This is something which is completely independent of the strategy we use. Right, of the strategy we choose to measure our parameter. Instead, we want to look on this quantity, and this quantity H of B Bx, right? So this is now the entropy of the distribution we have. So the question you might ask, okay, but we now have two different things. We have last hour we considered the variance of the distribution, right? And we were deriving optimal strategies with respect to the variance. Now we see that Haleva bound naturally tells us something different. Tells us about the entropy of this posterior distribution, not the variance. Is there a relation between the two? Yes, this is what you might ask. And in fact, there is a relation in one direction. And it's also clear that there can only be a relation in one direction. And I think we'll prove it in the exercises, but the fact is, among all possible distributions with a fixed, no wait, how did it go? Yes, so if you consider all distributions, right, all probability distributions with a fixed variance, there is one, right, which minimizes, among all possible distributions, probability distributions with a fixed entropy, there is exactly one distribution which minimizes the variance. And this distribution is, if you make a guess, well, it's a Gaussian distribution, right? So, so this is the message here, and I'll make a proof for the exercises. It's actually a general knowledge which is, I guess, useful, right? To know that there is a relation in this direction. So, but the claim now is that for let's write it properly. So consider all probability distributions P of B such that, right, the entropy of P of B is larger or equal than a constant H, right? Then the minimal, then from this, the minimal variance is given by the Gaussian distribution. Variance is given by the Gaussian distribution. Yes. The Gaussian distribution. So the Gaussian distribution is in P of B is equal to 1 to 2, right? The usual formula. B minus B mean value squared over 2 sigma squared, and it's equal to, now it's a bit complicated formula, but I'll just write it down from the note. Here we go. So write the variance. So variance of PB is equal to the sigma square, right, for Gaussian. And this is, let me just didn't write it out now this time, so they could use it on the phone, but it's slower. So this variance is given by the sigma square, and this is in fact equal to the following thing: exponential of 2h divided by 2 pi over e. Yeah. So we can write it like this: -1. Nice. Yeah. This is. I think you prove it in the exercise because it's a very nice result in general to know that the Gaussian distribution is nice because it gives us the minimal entropy for a fixed variance. Okay, but in our context, it's now nice because now instead of just right, so since we know that H, the entropy of the distribution is, let's put it that way. So now we know that the variance of a probability distribution is in general bigger or equal than this formula, all right? 2h minus h probability distribution minus 1 divided by this constant, 2 pi. Then it means that our Kolevo bound, which we just derived, also tells us something about the variance of the posterior distribution. Yeah. Why is it like this? Because you remember we had a bound on h0 minus sum of p of x, right? So this the Kolevo quantity was, so this s of gamma is bigger or equal than h0 minus sum of p of x, h of x, sorry, h of p of b, now in x, right? But in fact now this we can write it as in the following way, we just pass it on the other side, so we have sum of p of x because this here is this is a monotonically increasing function, right? This variance of the p of x. So we get that the variance of p of v of x is larger or equal than this story here. Larger or equal than the entropy of h0 to h0 minus s of gamma. So I write this one. Wait. Yeah, there is this. Yeah, no, wait, this is not yet this, right? Because we need to take care of the convexity with this probability. So let me write down what I want first. So what we have is that certainly what we have certainly is that the sum of p of x the variance of p of x. So the variance of p of x, p of b conditional to x, right? This is bigger or equal than this h of p of b conditional to x. So minus 1 divided by 2 pi, right? Now what do we want here is the following thing. That so the here before. Let's look at the average variance. So we say sum of p of x. So we'll put sum here. Sum of p of x. Variance p of x here. Now what we want is to say that this thing now is 2 pi sum of p of x exponential of 2h p of b conditional to x. Right? And we want to show that this probability can be put up there. And how can we show it? Well, we can show it by the fact that so if you plot the function, the exponential is a convex function, yes. So you see, so look at this thing, right? This thing here. So the exponential is like this. So if you take the average, so this sum of p of x, so this is the average of the exponential values of the entropies, right? So this lies here always, right? So we average the function, right? And we see that this is bigger than the average, the value of the exponential for the average function, yes? So clearly, because this function is convex, right? So it's shaped like this. The sum of the exponential of p for each value of x is clearly larger or equal, so it's always above, here. So all the sums, convex sums, they're always above than just exponential of sum of p of x 2 times entropy of p v of x back divided by 2pe, right? And this is something we know how to bound, because this we bounded just by the whatever quantity. So, right, so in summary now, this thing now, if it use it again, is again now just bounded by exponential of 2 times h0 minus s of gamma divided by 2pe. Yes? So, what is nice is that the Kolyeva bound, actually, and we'll end with this, I think, we don't have time to go further today. So the Kolyeva bound, right, tells us about, since if we know if we know our model, so we know this rho b, and we know the probability of 0, okay? So we know have the prior distribution, and we know the parametric model to get the state rho b, how it looks like in terms of the parameter. compute this operator gamma, which we already seen last hour, and this is just the average density matrix. Yes, and in fact, it tells us that so the entropy drop, how much information can Bob extract, can Bob learn, right, on this thing. So it's given by the mutual information minus the sum of px. This is entropy of this story. And conditional, right? This is bounded by just the entropy of this average state. Yes, but because Gaussian but because we have a bound on the variance from the entropy, we can use this bound to our purpose, because we care about the variance, to set a bound on the minimal possible variance, right, in this estimation scheme, right? But just bounding this term here. So, and this allows us to tell something, right? So, what I kind of promised in the beginning of the hour is that, yeah, right, we know that the fish information of the state is important, okay? So the fish information, so for the estimation, right, so far we've seen that the fish information of the state at this point is an important figure of merit, which tells us how ultimately precise we can do the estimation. Now we have another story here, is that if we really do kind of a Bayesian estimation, so we just once estimate a thing, because this is what we're doing here, right? We're given a state, we measure it, and we want to update our knowledge. Ultimately there is another limit here, right? So because this variance cannot be lower, that's something set, that the limit set by the entropy, right? By this entropy of the average state. So by how, actually this quantity here tells us how much information can a probe encode. Is the best, because we've seen it's actually limited by just the log of the dimension. So now for Bayesian estimations, there are kind of these two different things which has to meet in order to the state to be a good, for the protocol to be good, or for the state to be a good probe state. Yes, it's a high sensitivity, right? So a high sensitivity to small deviations, which give us a high Fisher information, so that the fidelity moves fast when you move along the curve, basically everywhere. And this entropy of gamma should be large. Yes. Now we didn't have time to discuss much about what this tells about the state, but in fact, if what we're going to do next is that we're going to see that again entanglement also helps from this perspective. So if you have entangled probes, they can encode in fact much more information, again quadratically more than if you have just product probes or separable probes. Okay. Yes. So again, from this perspective, we have a huge boost from entanglement, and so so that's kind of a nice feature. Not only entanglement helps increasing sensitivity of a probe state, but also it helps increasing the total amount of information you can encode in such an estimation scenario. Alright, so I thought of doing it today, but now there is no time. But yeah, it's not a problem. I will just start with this next time. And yes, see you